This is the second video that I'm making for a pre-calculus / math analysis type class, and we're still talking about functions. So here I have some basic toolkit functions that you might see throughout pre-calculus and beyond. We have y equals x squared, y equals x cubed, y equals x to the fourth, y equals the absolute value of x, y equals the square root of x, y equals e to the x, and y equals sine of x. Now, if you're just getting into pre-calculus, you don't need to know all of these off the top of your head. However, I would pause it and take a note because I'm sure you'll see them at some point throughout your time in math. Okay, so let's move on from these and we'll get to some transformations of these graphs. Okay, so here are the three different types of transformations you can apply to a function. First, we have shifts. Shifts are any movement up, down, left, or right of a function. Then we have stretches, and stretches are any elongation, whether we're stretching it like up and down or stretching it left to right of a function. And then reflections are any flipping of a function. So let's start with shifts, and then we'll move into stretches and reflections, and then we'll end this video off with an example. Okay, so here we have an example of a couple of shifts of a function. So here we have our parent function, f of x equals x, and this is just a straight line that goes straight through the point 0, 0. When we plug 0 in for x, we get 0 back. When we plug in 1 in for x, which would be about the point right here, we get the point 1 back for f of x. Okay, but now we have a shifted function. And this shift is taking x and shifting it to the left 2 units. How do we know it's to the left? Well, shifts happen in the counterintuitive direction. So when we add 2 inside the parentheses here, it shifts it to the left 2 units. Same thing over here. When we replace f of x with f of x minus 2, instead of moving down 2 units, we move up 2 units. So all shifts occur in the counterintuitive direction. Let's look at an example, and then we'll move on to stretches. Okay, so here we have an example that tells us to sketch the graph of x minus 2 all squared. Okay, so first let's start by drawing our parent function. From before, we saw that the parent function looks like this. We call this shape a parabola, and it's the graph of y equals x squared. From here, we want to notice that shifts occur in the counterintuitive direction, and we're replacing our x squared here with an x minus 2 here inside the squared. So that tells us that we want to shift this parent function 2 units to the right, and that's because we replaced x with x minus 2 here. If we replaced our f of x or our y with y minus 2 here, then it would shift 2 units upwards. But here, we're shifting to the right because we replaced x inside the parentheses with x minus 2. So let's go ahead and draw that out. So I'm taking our point 0, 0, and I'm moving it 2 points to the right. So this is going to be the bottom of our parabola. And it'll look like that, which looks a little messy, but our parabola is centered at the point 2, 0. And this is the graph of y equals x minus 2 squared. Okay, let's take a look at stretches. Okay, so here we have a stretch of a function. And remember, a stretch is any elongation of a function. So here we have our parent function y equals the absolute value of x, as we saw before in our toolkit functions. And we want to stretch it by a factor of 2. And we replaced x inside this absolute value symbol here with 2x over here. That means we want to stretch it in the x direction. Stretches occur in the intuitive direction. That means if you replace x with 2x, it stretches it vertically, but if you replace x with 1/2 x, it stretches it horizontally. I put a picture of what y equals 1/2, the absolute value of x, would look like on the board, just so you guys can compare the three. Okay, let's take a look at an example problem of stretching a function. Okay, so here we have our example, and it tells us to sketch the graph of y equals 4 times x cubed. So let's again take a look at our parent function, x cubed. If you remember from our toolkit earlier, it looks like this. Okay, so now we want to stretch this by a factor of 4. And what we've actually done here is we've replaced this y with a 1/4 y, and then moved it over outside of this cubed. So we actually have 4 times x cubed. That 4 is not being cubed up there. Okay, so as in the example before when we had 2 times the absolute value of x, this tells us that we want to stretch this function vertically. So let's go ahead and do that. 0, 0 remains the same, When we put in 0 for x here, we get 4 times 0 times 0 times 0, which gives us back 0, so that point stays the same. However, this graph is going to get pulled up a little bit up here and pulled down a little bit down here. So it'll look a bit like this. Now that we've got that done, let's move on to reflections. Okay, so here we have an example of some reflections. So first, I want to take a look at our parent function, which I'm using the absolute value of x again. And now I want to flip this function over the x-axis. So this line here, I want to flip this function over like this. So what I do is I replace y in this with negative y over here. So that means that reflections occur in the counterintuitive direction. So when you replace y with negative y, you flip over the x-axis. But when you replace x with negative x, you flip over the y-axis. Okay, so in this picture, I flipped over the x-axis by replacing y with negative y. And in this picture, I've replaced x with negative x, and I flipped over the y-axis. But notice nothing actually changes, because when flipped over the y-axis, this line becomes this line, and this line becomes this line. That's because when you take the absolute value of a negative number, it becomes positive. So the absolute value of negative x is the same thing as the absolute value of x. Okay, so let's finish off this video with one big example. Okay, so this is our example, and it tells us to sketch the graph of f of x equals negative 2 times, in parentheses, x plus 2 squared. Okay, so how do we want to start this? Well, let's maybe draw down our parent function, which is pretty apparent by this squared up here in the exponent and the fact that x is inside the parentheses here, that our parent function is going to be y equals x squared. Like that. Okay, so then what's the first transformation that we want to apply? Let's work from inside to out. So first, let's apply this shift right here for this plus 2. And that tells us that we want to shift this graph 2 units to the left, because shifts occur in the counterintuitive direction. So adding 2 moves us to the left. So let's go ahead and do that. 1, 2 to the left. That's going to be our base of our parabola. And it'll look something like that. Now let's continue working outwards, and we have this stretch here. And remember, stretches occur in the intuitive direction, so we want to stretch this graph by a factor of 2. So our graph will look something like that. And let's denote down here what these graphs actually are. So here we shifted this graph 2 units to the left. So this is y equals x plus 2 squared. And then over here we've stretched this by a factor of 2. So that gives us 2 times x plus 2 squared. Okay, so we've run out of room on this board, but on the next board we're going to take this graph and transform it with this final reflection up here. So on the last board, we finished with this graph of y equals 2 times x plus 2 squared, but now we want to flip it because of this minus sign right here. Which axis do we want to flip it over, you might ask? Well, because this minus occurs outside of everything, that means that we actually replaced f of x with minus f of x and then multiplied everything by negative 1. If we were flipping over the y-axis, then we would replace this x inside the parentheses with negative x. Okay, so this tells us that we're flipping over the x-axis, so we want to flip this graph down here. So let's go ahead and apply that. And so our final graph will look like this. Like that. And I think that's enough for now.